This is a test that's called the test for a single variance. It's often used to test a claim about a standard deviation, and that's just because the standard deviation is the square root of variance. There are some requirements that we need to do a hypothesis test for a single variance. We need randomly selected samples. The population must be normally distributed for the random variable, and we do need independent observations. So let's look again at the penny example. Pennies are minted with a standard deviation of 0.0165 grams. New equipment was purchased to improve the quality by reducing variation in the penny weights. A simple random sample of 10 pennies is obtained from pennies manufactured with the new equipment. A histogram shows that the weights of the pennies is normally distributed. The sample of 10 pennies has a standard deviation of 0.0125 grams, and at the 5% significance level, let's test the claim that the new equipment is effective at reducing the standard deviation in the penny weights. Okay, so we're asked to test a claim about standard deviation. This should tell us that we should be looking at the chi-squared distribution. Now, to do that, we are going to make sure that we have to have a random sample. So we do have a simple random sample, and the random variable is normally distributed, so we're okay there. And there'll be independent observations of these individual pennies. So what is the claim here? Well, the claim is that the new equipment is going to reduce the standard deviation. So the new standard deviation for the population will be less than what we have originally, which is 0.0165 grams. Okay. Since we're looking at reducing, it is strictly less than. This will be our claim. So our claim is less than 0.0165. Since it does not contain equality, this becomes the alternative hypothesis, that the standard deviation is less than 0.0165, which means the null hypothesis will contain the opposing view and equality, that sigma is greater than or equal to 0.0165. Okay, now we're looking at the level of significance. We were told at the 5% significance level, so alpha will be equal to 0.05. And this will be a left-tailed test. We get this from the alternative hypothesis, HA, that says sigma is less than 0.0165. Okay, so we're going to have a little bit of work to do because our chi-square distribution is a right-tailed test and this is a left tail. So we'll just have to do some modifying. All right, so let's look. What would we like to see? Well, we want the significance level to be 5%. So at some point, now this is a left tail, so inside of here, 0.05, we're going to need to find this critical value. Okay. So we can use the table. From the table, we'll be looking for the chi-squared variable. Now that measures to the right, so we're looking for chi-squared 0.95. And to do this, we also need to know the degrees of freedom. The degrees of freedom is n-1, which in this case is 10-1, which is 9. So once we look this up on the table, then we have chi-squared. Our critical value, the 0.95, will get us to 3.325, which belongs here, 3.325. Now, we also have to find our test statistic. This is the value of chi-squared that we will be testing with. So chi-squared is equal to the degrees of freedom, n-1, times the sample standard deviation squared divided by the population standard deviation squared. So if we fill this in, we get 19 times the population, the sample was 0.0125. We'll square that over sigma, which is 0.0165. That will be squared. And when you put this in your calculator, you should come up with 10.90. Okay, so we put that on our diagram, and using the critical value method, it's very clear to see that this value of our test statistic is not in this critical region. It is not, so therefore we're going to end up not rejecting our null hypothesis. But we can find the p-value of the test statistic. So if we were to find the probability that chi-squared is greater than 10.9, this would be putting it into our calculator. We could use chi-squared, the CDF, and so this would be 10.9 up until infinity with 9 degrees of freedom, and that would give us 0.2826. So that's going to tell us this probability here. Now it's a left-tailed test and we're looking for 5%, so it's pretty clear that the complement of that is greater than 5%, but we'll just show that. So the complement is 1 minus 0.2826, and that's 0.7174. So it doesn't matter which way you do this, either the p-value or the critical value. Either way, we are not going to reject the null hypothesis. We can summarize that because the p-value 0.7174 is greater than alpha, which is 0.05, or we can do it because the test statistic 10.9 is greater than 3.325. The point here is that it is outside of the critical region. And now we can interpret and translate this conclusion into our formal sentence. At the 5% significance level, there is not sufficient evidence to support the claim that the new equipment reduces the standard deviation in pennyweights.